Hi, this is our second video about equilibrium expressions, or capital K. And I like to call these special equilibrium expressions, or special Ks. And so they are Ka, Kb, Ksp, and Kw. Now it is still exactly the same concept, the equilibrium expression, which is the products over the reactants raised to the coefficient in the balanced equation, but these are kind of special cases. So the K, and then it has a subscript A. It's called the acid dissociation constant. It's how much the acid comes apart or dissociates in water. Now, strong acids will completely dissociate, so their Ka is very large. So there are those 7 strong acids, and when you put them in water, they will completely dissociate. They make all kinds of ions, and that's why strong acids are strong electrolytes. Okay, so please know that strong acids completely dissociate. What that means is that they come apart. They make the ions, so like hydrochloric acid, when you put it in water, there's a bunch of H+ ions and chloride ions, and so strong acids make a lot of ions, so they are strong electrolytes. And that large Ka lets you know that they're strong electrolytes. Weak acids only partially dissociate, or they only, a very small amount of them come apart, and their Ka is small. It's usually less than 1. So for our strong acid, let's go ahead and we'll say hydrochloric acid here, and it forms H+ plus Cl-, and so the Ka for that, and this would be aqueous. The Ka would be the H+ and the Cl-, the products over the reactants, and it is a really big number, which means it's all products. All right, now here's the Ka for acetic acid, and it is not one of those strong acids, and here's the proton that it's going to donate. So when we put it in water, the acid, this proton, Bronsted acid, donates the proton to the water, and it forms the hydronium ion. H3O+ is called hydronium ion, and it forms the acetate ion. But the Ka for this is 1.8 times 10 to the -5th. So let's write the Ka expression. It's equal to the hydronium ion, that's a product. The acetate ion, that's a product. And it's raised just to the first power because there's no coefficient, divided by the acetic acid. And we don't put the water in there because it's a liquid. And this Ka is very, very small, 10 to the -5th. What that means is most of what's in the reaction is the proton is on the acetic acid. So this Ka means that there is little ionization. So there are fewer ions in solution. And so weak acids are weak electrolytes. Weak electrolytes. There are less ions in solution. Okay, now Kb, it's a reaction with a base in water. And so this right here may not quite look like a base to you. It doesn't have the hydroxide as part of its structure, but it is going to accept a proton from water, and it's going to form, this is going to form its conjugate acid here, and look, like Arrhenius said, the base formed hydroxide. And the Kb for this, the expression would look something like this. This is called methylamine, has a +1. Then we got the hydroxide ion. Yep, it's a base. It made hydroxide in water, and it's over CH3 and H2, And there we go. This Kb is 10 to the negative fourth. And what that's telling us is that, well, we didn't make a lot of products. The K is a lot smaller than 1. We did not make a lot of products. This number up here, these concentrations are small, so we're going to have few of those ions. So weak bases are weak electrolytes. Few ions mean weak electrolyte. All right. Kw. Well, this is the auto-ionization of water, and it's where water acts like an acid and a base with itself. So one water molecule donates a proton to the other, forming the hydronium ion and the hydroxide ion. And so the Kw at room temperature for water is equal to 1 times 10 to the negative 14th. All right, so that is at 25 degrees Celsius. All right, now, what is this useful for? When would we ever use this? If somebody gave you a proton concentration, and something we've not talked about before is this hydronium ion is the same thing as a proton concentration. It just has water added in. So if they give you a proton concentration or a hydronium ion concentration, using a Kw, you can get a hydroxide. Or if they give you a hydroxide, you can get the proton concentration. All right, Ksp, this is known as the solubility product. It's how soluble an ionic compound is in water. Now, we really learned that silver chloride is not soluble in water. But here's an expression, your equilibrium reaction. And so the Ksp is equal to our silver ion times our chloride ion. And the silver chloride does not go in the denominator because it's a solid. That Ksp is 1 times 10 to the negative 10th. It's very, very small. So what does that tell you about these products over here? It means we don't have very many products in solution here. And so when we say that silver chloride's not soluble in water, it's really not. These ion concentrations are very small, as shown by the Ksp. Well, those are our special Ks. And so again, they're calculated the same way. It's products over reactants, but they can tell us a little bit about like how strong an acid is or how soluble something is. And it can be useful, like the Kw, in determining a proton or a hydroxide ion concentration in solution. So some special Ks.